Welcome to qnawire.
Hi. So the present problem deals with cell membranes. We are given that a cell membrane typically has a thickness of 7.5 nanometer. So let me draw a cell membrane. So let us imagine this is a cell membrane which has a thickness of around 7.5 nanometer. That's the typical thickness of the cell membrane, 7.5 nanometer. And we have the positive and negative charges distributed on two surfaces of the cell membrane like this. So we have the outer axon and the inside axon. This is the outside. This is the outer axon. And this is the inside axon. So this is the inside part of the cell and that's the outside part. So in the problem, I've already told you the typical thickness of the cell membrane is given to be 7.5 nanometer. And it is given that the cell membranes are partially permeable to allow charged materials to pass in and out through them. And so because of that, equal but opposite charge densities, they build up on the two sides of the cell membrane. And this charge, they prevent additional charges from passing through the cell wall. So this is the use of the cell membrane in this way. So it's given that we can model a cell membrane as a parallel plate capacitor with the membrane itself containing protein embedded in organic material to be as dielectric constant of about 10. So we can think of this cell membrane as a parallel plate capacitor with the protein embedded in the organic material as the dielectric constant material with a dielectric constant of around 10. So we can imagine this as a parallel capacitor with dielectric constant K, 10. And with this information, we need to find what is the capacitance per square centimeter of such a cell wall. So we know that for parallel plate capacitor, the capacitance is given by, so C equals K epsilon naught A over D, where K is the dielectric constant of the material in between the parallel plates of the capacitor. So C equals K epsilon naught A over D, and we need to find the capacitance per unit square centimeter of cell wall. So that means the capacitance per unit square centimeter. That means the capacitance per unit area of the cell wall. And this value can easily be written as K epsilon naught over D. So we already know all these, the values for all these terms. So the dielectric constant is given to be 10. We know the value of epsilon naught, which is 8.85 times 10 raised to negative 12, and the distance between the two sides of the cell wall, which is 7.5 nanometers. And if we calculate this value, so this value comes out to be around 1.2 microfarad per square centimeter. So this is the final value. So this is the capacitance per unit square centimeter of the cell wall. So this is the answer for the part A of the problem. This is part A. And moving ahead to the part B of the problem. So in the part B, we need to find, so it's given that in its normal resting state, a cell has a potential difference of around 85 millivolt. So the potential difference between the two ends of the wall is given to be 85 millivolt in its resting state. So the potential difference between the two sides of the cell wall is 85 millivolt. And given the potential difference, we need to find the electric field inside its membrane. So for parallel plate capacitor, we very well know that if the potential difference between the plates is given, then the electric field can simply be found using E equals V by D, where D is the separation of the plates. So the potential difference is given to be 85 millivolt. So it's 85 times 10 raised to negative 3 volts divided by the distance between the plates, which is 7.5 nanometers. So 10 raised to negative 9. And if we calculate this value, it comes out to be 11 megawatt per meter. So that's the value of the electric field in between the two sides of the cell membrane. So this is the answer for the second part of the problem. And with this, we have finished the problem. Thank you very much.